In this video, I'm going to go over how to calculate the parasitic drag coefficient for a plane and how to break it down across each of its various areas and components. So first you want to generate a CFX and then go to New Design Model or Geometry. After that loads, we want to import an external geometry file, which you can get from saving in SolidWorks. So you want to save it as an IGS or step file, both of which work. I'm going to use an IGS for this one, since it tends to work more of the time. Then after I generate my plane, I'm going to set to select faces, and then select all of the faces that represent a significant size of my wings. Then I'm going to right click over that, go to name selection, apply the geometry, and name it to wings, and then generate it. And I'm going to repeat this step for all of the various components. So I'm next starting on the fuselage. So selecting all the various parts of that, all around it. This one tends to have the most faces and will count as a significant portion of the drag. This front part here might instead be characterized as part of the motor drag, but I'm going to include it in the fuselage for this, since I can just edit the math later. Making sure to get as many parts of the fuselage as I can. And now I'm going to get the corners around this on the tail boom, which I'm also deciding to count as part of the fuselage. You don't have to, but I'm going to. Zoom out for a final check, and then count the backside there. And then name this selection, apply the geometry, and name it to fuselage, and generate it. And then the horizontal stabilizers next. On your part, the horizontal stabilizer may all be one group, so you only need to select 3 faces perhaps. So name selection, apply the geometry. Make sure to do that immediately after the step, otherwise it could lose the geometry you had selected and you'll have to reselect it all over again. Now I'm doing the vertical stabilizer, and just for simplicity I'm naming it V-stab. Generate that, and then the landing gear, which will include all of the wheels and this piece here that attaches it to the fuselage. Yep, and you can see which parts of the landing gear are selected based on which ones are green, of course. You can also click on this blue ball here with the defined coordinate system in order to reset your view if you get too rotated into an odd spot. And it's now name selection, apply geometry, landing gear, generate that. And just to check over, we have the wings, the fuselage, the horizontal stabilizer, the vertical stabilizer, and landing gear. After we've done that, we can go to Tools, Enclosure, set it to a non-uniform size, and we can make pretty large cuts in the X value, since the air behind the plane is largely irrelevant to our drag, and give it just a small amount of space to normalize in front of it, which in this coordinate system is -x. We're going to give a reasonably large cushion in the 2 y directions to allow for the vortice effects over the wings. Oh, sorry, that should be in Z. And then y is the vertical space, so we're going to change that to 3.3. And then we can generate it to check our work. And that seems like a reasonable size for our box to contain it. And if you don't like your size and want to edit it, you can go to Edit Selections to change it. Next, we're going to create a Boolean, set the operation to subtract, set the tool bodies to the, target bodies to the air around it, apply the geometry. And for tool bodies, we're going to go to the parts and bodies and select all of the ones that are not the air and apply that. Preserve tool bodies is set to no, and then we're going to generate the Boolean. As you can see, all of our name selections are still preserved. So we're going to save this and give it a name. I'm going to name it Paradrag2, since this is the second form I have of that style in my current folder. And since our geometry is all good, we can start refreshing the mesh step. Sometimes the various sub-elements refuse to close in time. So we wait for the mesh to refresh, and then we can start editing it. Now that we see the lightning icon, we can right-click and go to Edit. So first we're going to try generating it without editing any of the default settings. However, we have ran into an error, so we're going to edit various elements. Okay, so now we have successfully created a mesh. These are my final settings. Feel free to pause the video and use these. These are pretty good. It took me a while to get to these. So then I'm going to save that. And then here's what it looks like from behind. And then we're going to exit out of that, right-click over our mesh, and update. Once that's finished and we get the check mark, we can double-click on Setup. Now we're going to create an inlet boundary and select that front face, then our boundary details. The normal speed I will set to 32.5 meters per second. This is based on an estimate I got. You're going to need to be somewhat close to it to keep the Reynolds number approximately correct. However, the coefficient corrections we're going to do later should take care of slight inaccuracies. So next we create the outlet, we click in location and select the back box face and set the relative pressure to 0. Now we're going to create a fluid walls boundary, set it to wall, and then select the various locations around the plane that are not the inlet or outlet. We're going to set that to a free slip wall and OK that. So now we're going to create a boundary for our wings. We will set it to wall and no slip wall, rough wall, and set the sand grain roughness to 0.2 millimeters. And OK that, and we see it appear here. We're next going to create one for the horizontal stabilizer. Setting it to a wall, no slip wall, rough wall, 0.02 millimeters. So I'm going to do these for all the lifting surfaces based on the material that I chose for the for that surface. Next, the V-stab. So if you're creating your own plane, you should do research on what the likely sand grain roughness is at each of those locations. And we need to do each of these individually so that they properly show up in the results step. So next we're going to create one for the fuselage. And when you type in the name exactly, it auto-selects the location. So for this one, I'm going to set it to a 1 millimeter sand grain roughness for the fuselage. And the landing gears next. Setting it to a wall with a sand grain roughness of 1 millimeter as well. And so now we can see we have the wings, vertical stabilizer, landing gear, and fuselage and horizontal stabilizer all as well. So we're going to save that and move on to the solution. So I'm resetting the solution since I previously did this with a different setup, but you should be able to just double click on the solution to get it started. And I'm going to start the run. So once the variable value drops to 1 times 10 to the negative 4th, the fluid flow should complete running, which we can click OK on and close. Then we can double click on the results or edit them in order to view them. Make sure your solution report is checked true, and then go to Report Viewer. And here we can see all of the momentum and force changes on all of our surfaces. You may need to refresh these if the values do not show up. If we go back to the 3D viewer, we can check all of these surfaces to see what they include. And so now I'm going to input all of these values into a table and show how to calculate the parasitic drag coefficient from each of the surfaces. Here you can see all of the components and their corresponding drag forces listed in this table. And I've also written in each column the area of the wings, which is just the span times the chord, the velocity simulated, the estimated air density, and so the coefficient of drag is calculated as twice the force of drag divided by the area times the velocity squared times the air density, as you can see here. And then I totaled all of those elements together and multiplied them by a crud factor of 25%. This is done because simulations tend to underestimate the drag forces, so we multiply it by an extra 25%. The coefficient of drag induced is all of the non-viscous effects that we're going to get from the lifting forces of the wings, which I can show you in XFLR5. I'll edit in here a picture of how I got the coefficient of drag as 0.009, induced anyway. And then, so the total parasitic drag is this total amount of the coefficient of drag factors added together times the crud factor minus the induced amount. And so this gives me the total parasitic drag coefficient.